Again, thank you for the invitation. We have started robotic synthesis of semiconductor materials since 2019, and this is kind of new as compared to high throughput automated synthesis of biological samples and organic chemistry and those kind of things. Here I want to show you an examples of the pipetting, micropipetting, automated micropipetting system that we use to deposit either thin films of metal halide perovskite, which are one of the breakthrough materials for solar cell application, as well as many other optoelectronics. This is an example of the high throughput automated synthesis of quasi 2D hybrid perovskite that we used. Basically, this workflow in order to explore the growth mechanism of these quasi 2D materials. So here is basically the 96 dwell plate, a combination of 3D, three-dimensional metal halide perovskite and 2D metal halide perovskite in 95 or 96 different composition ratio. Then after that, we do the automated high throughput optical spectroscopy in order to gain some knowledge about their band gap and other emission properties. Next, we do the automated peak fitting. For example, here we have generated over 3,000 optical spectra, and then we implemented the automated peak fitting in order to study and to explore the phase growth of these quasi 2D materials. Next, I would like to actually show you what is the workflow in my lab, because in our opinion, one of the most important element of the automated synthesis lab is the workflow. Obviously, this is in academic scale, is different from the industry scale. So here, obviously, we start from the agent. We have the automated high throughput synthesis of the microcrystals and the automated characterization. From those, we get some feedback, and we can choose and select those interesting compositions to make either single crystals or thin films of those semiconductor materials for different optoelectronic application. Each of them have different proxy measurements, whether they are single crystals. We have a different proxy measurement. If they are thin films, we have different set of characterization suitable for thin film. However, the most important point here is that first of all, we need to define a language in every workflow, and the language that I define for my workflow is different from the language that other labs, which are even working on the same type of materials, define. So during this workflow, I make multiple decisions based on the feedback, and I have to be able to adjust my decisions dynamically. So basically, in this workflow, I can divide the workflow based on the ideation, orchestration, planning, and also implementation. As I mentioned, I receive multiple feedback. Based on those feedback, I plan the next set of experiments. I need to be very dynamic in terms of that. I need to look at the latencies, how long does it take, what is the cost, what is the reward and value function, And based on these, based on these parameters, my colleague and I basically.
Maybe another minute at most.
Sure. My colleague and I have defined several challenges for labs of the future that we think is important. First of all, as I said, we need to define the workflow based on a combination of human and robots. We believe that the labs of future cannot be only fully automated. It's a mixture of a human and robotic agent that is necessary in our opinion. Second will be designing the workflow, again, based on the decision of the human and the robot. And then defining basically the reward and value function, why we are doing that for a specific functionality or application. We need to integrate the reward function from different dissimilar domains, for example, computation with the experimentation. And the last two are basically mostly related to the machine learning from my collaborator. We need to have a hypothesis-driven experimentation for our automated workflow and even generate that, which is beyond the human, and make the machine learning, according to them, very interesting.